Tennis balls are replaced every 7 games in pro tournaments. But why? That neon yellow ball might look simple, but it's anything but. It's the product of decades of research, engineering, and relentless testing. A multi-million-dollar obsession hidden in plain sight. At the highest levels of tennis, the ball has to perform flawlessly. Whether under the desert sun at the Australian Open or the damp chill of Wimbledon, consistency is everything. Manufacturers pour millions into creating a tennis ball that behaves the same in every match, on every surface, in any climate. From the bounce to the felt, from pressure retention to flight stability, each element is carefully engineered, and it all adds up. Let's explore why making the perfect tennis ball is a science-driven, high-stakes endeavor. Material science. First, it starts with what the ball is made of. At its core is a hollow rubber shell, a carefully calibrated blend of natural and synthetic rubbers. The composition must balance 3 things: bounce, durability, and pressure retention. Too soft, the ball feels dead. Too hard, it's uncontrollable. Inside that shell, compressed air or nitrogen, pressurized to about 14 pounds per square inch above atmospheric pressure. That internal pressure gives the ball its liveliness, but it leaks out over time, which is why even unused balls can go flat. Then comes the felt, the fuzzy outer layer. It's made of wool and nylon blended in specific ratios. The felt slows the ball's speed, controls spin, and dictates how it grips the court. On hard courts, the felt wears faster. On grass, it slides more. On clay, it picks up dirt and moisture. Even the adhesive used to bond the felt to the rubber is part of the performance equation. A tennis ball is a layered, engineered product, and each material has a role to play. Consistency is everything. In professional tennis, consistency isn't a luxury, it's a necessity. Players train for years to master the feel, flight, and bounce of a standard ball. A variation in speed, weight, or bounce, even a tiny one, can alter timing, strategy, and confidence. That's why the International Tennis Federation sets strict standards. Weight, 56.0 to 59.4 grams. Diameter, 6.54 to 6.86 centimeters. Bounce, must rebound between 135 and 147 centimeters from a 254 centimeter drop, and must deform within a precise millimeter range under pressure. To meet these specs, manufacturers use laser calibration, pressure control, and robotic quality checks. Tournament balls are made in smaller batches under tighter controls than retail balls. In a sport of millimeters and split seconds, a single inconsistency can mean winning or losing. Extreme testing. Creating a perfect ball isn't just about designing it, it's about testing it. Wind tunnel testing measures aerodynamic drag and lift, helping engineers understand how the ball travels through air. Too much drag, the ball slows down. Too little, it becomes uncontrollable. Robotic machines simulate thousands of serves and smashes, replicating wear and tear under match conditions. They monitor how the ball flattens, how the felt wears, and when performance starts to drop. Climate chambers expose the balls to heat, cold, and humidity because a ball in Melbourne behaves very differently from one in London. And pressure retention tests monitor whether the ball stays lively for hours, days, or weeks. Only the best balls survive this gauntlet. Most fail before ever making it to a pro court. Environmental cost. But there's a downside to this level of engineering: waste. More than 300 million tennis balls are produced every year. Most end up in landfills. Why? Because the rubber is vulcanized, a chemical process that makes it nearly impossible to recycle. And the felt? It's mostly synthetic, non-biodegradable, and tightly glued to the rubber. Even practice balls used for a few hours are often tossed. Some initiatives are trying to change that. Used balls are being repurposed into court surfaces, flooring, or even donated to schools and animal shelters. A few startups are developing biodegradable options, but replacing high-performance materials without sacrificing quality remains a monumental challenge. The perfect ball comes at a price, not just financial, but environmental. Behind every Grand Slam is a branding battle. Wimbledon has used Slazenger balls since 1902. The US Open uses Wilson, the Australian Open, Dunlop, and the French Open, also Wilson, after switching from Babolat. These aren't just logo placements, they're multi-million-dollar sponsorships with custom balls designed for each surface and climate. Players, coaches, and fans build muscle memory around how a brand's ball feels, spins, and bounces. That brand association drives global retail sales, which is why manufacturers guard their formulas like trade secrets, investing tens of millions into professional perfecting a ball that might one day serve match point on center court. Unexpected fact, Wimbledon's 20 degrees Celsius rule. Here's something few fans know. Wimbledon stores its tennis balls at exactly 20 degrees Celsius or 68 degrees Fahrenheit. Why? Because air pressure changes with temperature. Cooler balls bounce less. Warmer ones bounce too much. Just a few degrees can change a ball's behavior. By storing them at a constant temperature, Wimbledon ensures every ball feels the same, whether it's used in the blazing sun or under the roof on a rainy day. That's how seriously tournaments take the ball's integrity. So the next time you see a ball kid hand over a fresh can of tennis balls, know that you're watching the end result of a global, precision-obsessed R&D project. From high-performance rubber to pressure calibration, from climate testing to spin dynamics, it's all part of the design. Because in elite tennis, there's no room for compromise. One bad bounce could mean one bad point, which could mean one lost match. And that's why a tennis ball, simple as it seems, can cost millions to perfect. If you learned something new, give us a like and subscribe to our channel. Let us know in the comments, did you ever imagine that something so small could be so complex?